EU-IoT website. So I kindly ask you to start recording. We got the consent of all speakers. And of course, we will let all registered participants know about the recordings. So without any further ado, as I said, this is the first of a series of seminars. Our topic today is artificial intelligence and Internet of Things at the edge, or if you want, edge machine learning. It's a very topical subject, it's a very trending subject, a very hot subject in the area of Internet of Things and edge computing. So I'll take a few moments to introduce the topic and then give the floor to our excellent speakers that they are gonna walk us through machine learning at the edge with emphasis on different aspects of federated machine learning. So what we are discussing today, right? We know that we've got an explosion of data. Maybe in the last 2 years, the data that have been generated are more than the full amount of data that were generated ever before in history, the total amount of data. But we are also seeing a trend, and this is, for example, extensively discussed in recent events like Hannover Messe or the Industrial Internet of Things World, those 2 events last month, that a great deal of this data will be collected and they will be processed at the very edge of the network and not at the cloud. So there were, people discussing that in the end, we're going to have just 20% of data in the cloud and 80% in the edge. And we are already seeing this trend. So moving the data from the cloud to the edge and creating ecosystems that are not cloud centric, but they are focusing on edge computing. And when you are at the edge, you've got different devices, different hardware platforms, different middleware platforms, and different ways to process data at the edge. Now, and the reason is that you've got different ways is that this is a trade-off game, as we will see, right? So depending on the level of security you want for the application, the level of power efficiency, the level of latency, the performance requirements, the level of privacy-preserving computing and privacy preservation, you've got different options. So we are going to cover today mostly federated machine learning and TinyML and embedded machine learning, focusing at both the hardware and the software or middleware. If you want, in future seminars, we have a future seminar which is on blockchain and decentralization for decentralized intelligence at the edge. And this is going to be a nice complement to today's seminar. So what we will discuss and what we will learn today, I have tried to make a quick list. So what is federated machine learning? How can I build an FML application or pipeline? What are the main cybersecurity issues in federated machine learning? And what are some of the real-time, the real-life use cases, practical use cases that FML adds value? Also, what hardware can I use for AI at the edge? And how does this accelerate the processing? We have presentations on this, right? And also, what is embedded machine learning? What is TinyML? And how can I run and how can I build and run a deep neural network or other form of machine learning on a microcontroller? So these are the things that we will cover in today's seminar, and you will hear shortly. And this is, I would like to go straight to our agenda and move also for the sake of time to the next presentation from the Assist IoT project, which is going to provide the introduction to the federated learning, so that later presentations on federated machine learning could build on top of it. So Marcin, I'll give you the floor. Please feel free to introduce yourself and your project, and we look forward to your speech and follow up pages on federated machine learning. Thank you very much. I'm John Soldatos, EU-IoT project, Intrasoft International, and I'm done speaking for the moment. See you later on the TinyML presentation. Marcin, the floor is yours.
For me to take the floor, I need somebody to let me share my screen, because at this moment...
Yes, I have to stop sharing. So
okay, let me do this. And the first thing is, I hope that you see my my screen, but just... Okay, so ladies and gentlemen, it's a real pleasure to be here. My name is Marcin Paprzycki, and I represent the Assist IoT project. And today I plan to say a few words that will be providing the background for the other talks that will be following. I hope that you see my first screen. So if you don't see my screen, then you should scream. And now you should see my second screen, which says distributed problem solving. You see it. Cool. Okay, so I wanted to start. Let's get to work. Let's assume that you have some computational intensive task. It can be, in general, it can be related to anything, but for us today, we are interested in machine learning. And this can be training neural network, nature-inspired optimization, anything that you want. And you have a very large data set. And if you try to complete it on a single processor or a single node or a single computer, I will try to use the word node, but it is node means a processor or a computer or a cluster, whatever it is. It can require really time. My students, when they are running some convolutional neural network on some picture sets, it can take 12 hours or longer to do one process of training. Okay, so it can and they are not using very large data sets that John was talking about coming to us in the future. We are talking about normal student master thesis type data sets that are in Kaggle or in some other places. Now, let's assume for a moment that you have multiple nodes available. And those multiple nodes can be processors within a supercomputer, but it can be a network of workstations, or you can have, and here is where I wanted to throw something into what John said. We should not talk only about cloud and edge. We are now we are entering the age of fog. Edge, fog, cloud, where in the fog you can have multiple nodes available. Then maybe there is a way to split the work in such a way that each of the nodes will be doing something, and then you will be somehow combining the results. When you combine those results, it can be that the process is over, you are successfully done, or it can be that you have an iterative process where you combine, split, and so on until you are happy. Now, distributed problem solving is a very old thing, because already before 2000, work was done in this direction. And for me, one of the worthy mentioning is a PhD thesis of Eric Cantu-Paz from University of Illinois Urbana-Champaign, who did this. He had the supercomputer at Illinois Supercomputing Center, and each node was running a genetic algorithm, and from time to time, the best genetic material was exchanged. Later on, it became known, and it is still known as island version of evolutionary computing. So as you can see, this is how it's done. Okay, you split the work, and from time to time, you somehow synchronize the results. This is the most general statement. Now, distributed machine learning, you can find here a reference, and those slides will be available. So there is on arXiv the work by Fairbacken, Volting, and others that summarizes distributed machine learning. And of course, parallel computing. I am getting old, and I started my PhD work in '87, and parallel computing was already starting to become a norm. So, what is important about distributed problem solving in general is that in most of the cases that are considered, we have a single owner of all the data, single stakeholder. Okay, so for instance, let's say that we have Siemens, and Siemens has a big factory, and in this factory they collect shiploads of data and they move it to the Siemens cloud. And in the Siemens cloud, they will be training some Siemens models to be applied to the Siemens process. This is fantastic. Maybe they will bring in some data, external data from some open source public data sets, but it's still gonna be everything is Siemens data. Okay. Now, keeping this in mind that we have this single stakeholder model, let's now reflect on the situation. We have now smartphones that have 10, 13, 15 sensors, and those sensors generate streams of data. Now, not only this, but we have very fast dropping prices of sensors and actuators. So you can have patches of sensors installed everywhere. You can have a city in which citizens will install their own sensors of air quality to know what's going on outside, and should they wear mask or should they not come out of the home or whatever. We have explosion of wireless network technologies, and here we have the 5G coming that allows you to set up connectivity between sensors, actuators, gateways, computing nodes in the fog. You can set up any infrastructure to realize any workflow of data between those elements. Okay. Now, we have, of course, a lot of progress in research in Internet of Things ecosystems. European Commission is pumping a lot of money into this area. We have new machine learning. We are learning more and more how to do machine learning on the large scale. And also, we're going to be talking later on about tiny ML, but you don't have to be so tiny. If you talk about, and this is just an example, I am not paid by Intel or NVIDIA, especially they are not European companies, but Intel has Movidius sticks. NVIDIA has Jetson Nano. So generally speaking, for around $100, so it would be for us around €100, you can stick a powerful neural network software into your laptop. Or you can place it in a gateway, or you can place it by the machine. Jetson Nano is a little board that you can add to almost anything. Now, this all means that the image of a single data owner is no longer valid. We need to understand that we are starting to live in an ecosystem of data owners. And now what happens? Look, if you have a small device like a cell phone, then applying large machine learning only on your data will only bring limited reward to you. But if you share it somehow, but not share it because you don't want your data to be shared, but you want somehow jointly to get an image that comes from multiple sources. Now, envision that people have collections of images, and let's talk about businesses. And we will have in a moment a use case where transferring all this data to the cloud is a problem. Then we have medical images, okay? They cannot leave the location. If the location is given hospital, then they will stay there. You cannot share them. So local data that belongs to different stakeholders. Now let's reverse it. Let's say that a lot of companies have Siemens machines, and they have data about Siemens machines in their environment. but they will not share this data because whatever is on those machines that are running in the context of their businesses is not shareable. So what can we do? Well, generally speaking, this is the answer that, of course, today for today's workshop is federated learning. So federated learning is about, and now this is the funky word, co-opetition. Co-opetition is a business people coming together, getting drunk, and figuring out that if they take cooperation and competition, splice them together, they're gonna get this cool word, and they will be able to publish 150 papers on co-opetition model in business. So federated learning is about co-opetition. So what we have? We have some initial version of shared model, then you split it. Each participant improves it and sends back parameters to improve the model, but only parameters, nothing about the data. Data stays safe. And then the new model, shared model, improved, is created, sent back, and the loop continues. Now, it seems like a distributed machine learning, but different rationale. Remember, only parameters for the model are shared, updates to the model, but not the actual data. Now, important. Majority of work is related to federated learning with neural networks. However, anything that you can use for distributed machine learning, you can also use for federated learning. You're just gonna need to tweak it up somehow. And I presume that in the subsequent presentations, for instance, Arne, who's gonna be talking about realizing federated learning, will tell you that, you know, you need to do this or that to take this and this machine learning model and turn it into a federated learning by specifying pipelines, specifying dependencies, and so on. Now, architectures for federated learning, there are many, and I deliberately put this just to give you here some ideas. Here is the basic model, which is master-slave. Here you have here you're gonna be combining the shared model. Here you have devices that each one is training its little sub-model, and it goes back and forth, back and forth, back and forth, and this shared model is improving. Here we have a more complex, and this is, by the way, from the work of Lee and collaborators, that if you have hospitals and medical data, you may want to have more intricate model of sharing parameters to make sure that the private data stays private. However, when you deal, for instance, with balancing the model, and I will make a comment about this in a moment, I just wanted to show you, look, you can have a more complex architecture. Because here you have clients that are connected with intermediate managers that are mediators, and only mediators will share the updates with the central federated learning server. Now, this immediately points to you that you don't have edge cloud. You clearly are moving towards edge fog cloud, where the mediators will represent in conceptual way the fog. Now, application areas. First is, of course, medical. Look, COVID, X-rays of lungs and hearts, people who survived, people who died. You have in each clinic, in each hospital, small sets of data, and you cannot get them all to the central cloud to run global model. They have to stay on premises. Preventive maintenance. This is what I already mentioned. Let's say that in Europe, you have 25 companies that have the same type of Siemens machinery. They each want predictive maintenance. So they want to be able to predict when the machine may have problems. But they are not ready to share any data about the actual usage of their machines. But they may be willing to do what the pharmaceutical companies are doing. Here you have 10 largest companies, pharma, who decided to work together with NVIDIA, probably using their Clara platform, to create Melody, which is the machine learning for drug discovery, that none of them will share their data. but they will be building shared model. Here is Assist IoT pilots. And briefly, we have a pilot with worker safety, and you may have heard already about it. So one of the things that we cannot share is private information about each worker. However, we can build model of predicting bad things happening to workers who wear protective gear and have some sensors in it. Private stays private, model is model. Cohesive vehicle model monitoring. Here, one of the things that we have is we have maintenance on exterior of a car, and we're gonna have zillions, if not gazillions, of photographs of cars, but they will be staying in individual locations across Europe. And not only nobody wants to share this data for business reasons, but sending all this data to the cloud and then paying for the cloud to process it. It's madness. Here we have port automation, and in the port automation, we will have different locations with crane from Kona Cranes, our partners, and we will have to improve models of image processing and container recognition within images. But to do this, you need to share not the data about specifics, but to improve the model. What are the research areas? Those are just samples. And the first one is, and I hope that my colleagues will follow up on this, which will be, what is the topology to be used in the training process? You already have three. There is more, and I presume that there will be more about it. I am even not mentioning attack because the next talk is about security in federated learning. I wanted to just mention something about data imbalances. Look, you may have a data set which all classes are balanced. However, because you are federating, you have an issue. Because, for instance, you may have different people have different handwriting, and they will be having samples of their handwriting on their phones. So each data set is totally different than all the other data sets. You have a problem. The next one is funky. Kangaroos are in Australia or in the zoo. If you don't have a zoo, you will never have a kangaroo in your image set. But if you have then plenty of photographs from Australia, there will be plenty of kangaroos. You have an issue. There is more here to it, but we are running out of time and I'm trying to be nice. So just a thing here. If you have data which is imbalanced, what you can do is you can share information, maybe share information about the classes represented in your data, sizes of your data and others, so data parameters, and then you can dynamically generate this infrastructure. And if you look at this picture, the key point is, look, each one of those 4 devices has different data, but if you combine them into a group behind single mediator, it's balanced. Here you have another mediator and you have not very balanced each one of them, but combined you get nicely balanced data. So topology and additional infrastructure software can help you. There are open source platforms for federated learning, at least 3, Fate, TFF, and PySift. And they have various, and by the way, this slide you will find everywhere. We not within the Assist IoT, but with Professor Maria Ganja and our master student, we started to develop our own little federated learning platform, well, not platform, federated learning environment, because the big platforms I showed you, they are all-in-one solutions, more or less. They are to be used. We want to develop something that is going to be more research oriented, to play with various scenarios. It is available on GitHub, and of course you are invited to join us. And I am on time because there is still 1 minute and 50 seconds for questions. But how to find me? You can find me on LinkedIn. You just put my first and last name, and there is only one Marcin Paprzycki in LinkedIn, I believe. Don't find me on Facebook because I am already filled to capacity on my both 3 accounts. There is my email. I am on Google Scholar. And by the way, if you have a would like to submit something to a conference, especially, don't forget about the May 24th deadline. If you are industry and you would like to submit a position paper to our conference, here is the name of the conference. So thank you very much. I stop here, and I think we have 1 minute, 10 seconds for one question. And then there was silence. I feel like in class. This always happens. I finish lecture and my students have no questions at all. So guys, are you like my students, or will I get one question?
Yeah, can you hear me?
Yeah, sure, go ahead.
Okay, so did I understood correctly that you mentioned it is madness to share the data on the cloud? Can you elaborate the statement?
I will. For instance, if you have so many photographs and your locations are spread geographically and they are behind slow internet connectivity, then sending gigabytes or terabytes of data to the cloud may not be the best thing to do. Okay, it is, and by the way, this was already in the first talk. We need to look carefully at the edge cloud model. It is not going to work. You need to do things as soon as possible within the chain from the edge to the cloud, because moving things to the cloud and the images from the Tutronic case are clear situation like this. And by the way, also, look, if you have Avis, Hertz, Eurocar, Sicht, and other, there are all those car rental companies. They will not share their data in the cloud. They will not share the images, because sharing those images with competition can divulge IPR that should stay private. So you cannot, not only you should not, because moving all this data makes no sense, but you should not share the data because there is business advantage knowledge in your data that you don't want to share. Okay? So I think I have to stop at this moment because I don't want to go. It's already 21 minutes. Mr. Chair, do I have time for one more question, or should we move on?
I think, Marcin, we are okay with time because I gave you 3 or 4 minutes from my time. So thank you very much, I think, for the presentation. So we've got also a question on, confidential computing. Also, I said some things about homomorphic encryption. I don't know, maybe if this would go to the next presentation.
I think that this is going to be covered in the next presentation.
The next presentation, which is about security.
Yes.
Just to take advantage of the time I gave you to take it back, is also a World Health Organization using some sort of federated learning for learning models in healthcare and also during this COVID time? Are you aware of this? World Health Organization or not?
I am not aware of this. I am also a little bit surprised because World Health Organization data on vaccination is outdated on their page, because it is 14 million for Poland for like 4 days, and we are far past 16 million. So I don't think that they are doing a perfect job on this. And of course,
but it would make sense, right, to learn a bit.
Of course, it would make sense to build models on global scale, but then you would need to have global scale federated learning platform. And this means that everybody who is an American QAnon believer would tell you that this is Bill Gates that trying to take over the world together with the Hungarian guy. They together conspire. So building global solution is a problem.
Okay, thank you very much, Marcin. So I think if you stop sharing, we can go.
Yes, I am trying to figure out. Okay, I stopped sharing. Floor is yours.
Thank you very much for the excellent introduction, insightful. If you are around, we're going to have a Q&A session in the...
I am planning to stick around because I want to see what the co-opetition is presenting.
Okay. Artemis, the floor is yours. Feel free to share your presentation and introduce yourself.
Thank you. Let me just share my screen.
Yes, we can see it, and we expect the full mode, right? Yeah, we're waiting for the full mode.
Excellent, thank you. So many thanks for having me here today. Many thanks for Marcin for the introduction. I'm Artemis Vulkidis. I'm from Synelixis, and I'm representing as a technical manager the AIoT engine project. So before starting, a couple of words about the project. Core scope is to develop an edge-based, let's say, hybrid cloud edge platform for assisting IoT services run smoothly and enable machine learning capabilities and blockchain ones for the devices, the edge devices that are, say, resource constrained, or they don't have the capability, for example, to develop new services based on in-house machine learning. So in this context, my presentation will have a very, very short introduction to federated learning. Thanks to Marcin, I don't have to say many things on that. Then we're going to discuss about protecting federated learning processes from privacy-related attacks. Some key methodologies which will be also described. And then we're going to check a totally different context, just to see also the other side. A couple of things on how we can employ federated learning towards offering active, let's say, cybersecurity services. So we're going to talk about some generative adversarial networks and some practical considerations. So an ultra short primer to federated learning. As Marcin also said, the biggest advantage of federated learning is that they can offer privacy. In what sense? The model is not shared. The data is not shared. It's just a model that gets shared. So this offers a notion of privacy, since the data collected from the edge devices, they remain private. And at the same time, what we would need would be that the network as a whole, the devices and the communications, they are kept secure from cyber threats and relevant attacks. Federated learning is a step towards that direction, because we're stepping out from the classical distributed machine learning, where the data over here, normally they get shared. But when talking about federated learning, the data stay on the IoT nodes or the aggregators, the edge nodes, as Marcin said. And it's just the model values or some updates on those that get traveling through the network. So the biggest advantage is that the decrease of the risk of unauthorized data access. Even if access gets compromised in a node, then it's just a subpart, so not the whole data, which is kind of important. We are also able to limit network traffic, since the training results are much smaller than the size of the data itself, and less resources than conventional distributed machine learning are needed, at least at the cloud part. Now, we talked about the federated learning, how it enhances the privacy and partially, let's say, security, but is this privacy preservation guaranteed? Yes, actually, no, it's not guaranteed. The reason is that although the data that get transferred are the model related solely, one can attack against this model, for example. So there are three basic types of attack: data poisoning, where it results to mislabeling and false labeling, model poisoning, and re-identification. We're going to discuss a bit about the first and the third in the next slide. So an example of an attack against federated learning. So that's data poisoning, and it basically refers to inserting false data during the training that can actually lead to false labeling. So an example is here we have, let's say, a federated learning model trying to understand about pandas. Then an attacker inserts the gradient descent, so the first, let's say, derivative of an image related to a gibbon. That could result in a panda image being classified as a gibbon. So that's the 101, let's say, example on data poisoning attacks. Next example is re-identification. Interesting part here is the following. If one may have access to the entire history of the model weights, and they have a data source that could resemble to the original one, then they could use these streams of model weights to identify partly, let's say, the original images that were used for the training. So that, of course, could definitely lead to a privacy leakage. So we just saw that privacy is not guaranteed, though it's, let's say, enhanced. Can we make the privacy preservation guaranteed? Short answer is yes. Not short answer is that we can use multiple techniques such as homomorphic encryption. I think it was already mentioned a bit in the chat. We may also use secure multi-party computation, which we are not going to cover in this presentation. And we can also go for differential privacy. Finally, there are some other hybrid methods using bits and bytes from both. Without losing much time, a few words about homomorphic encryption. So homomorphic encryption, what it does is that it practically allows the aggregation part of the federated learning servers or the aggregator to be performed directly on ciphertext. So the models are not, let's say, they do not travel in the network, plain text, for example, but they are encrypted and they're not unencrypted at any moment. This enables, of course, a participant to define function on encrypted values. But two disadvantages that lie over there is that there is the need of an external party to hold the secret key, which is, let's say, not standard in the FL setting. So this is mostly related to having trusted parties. And the second is that depending on the mathematical operation that gets applied on the aggregation part, this whole process can, in the end, be computationally costly. A practical example of that, you can also see the source at the lower side of the screen. As a first step, the client produces the gradients, as you can see over here. Suppose that this is, for example, an IoT node, powerful enough, or it is a computational node residing at the edge of the network, perhaps a digital twin operating on behalf of the physical device that we talked before. As a second step, these gradients, they get encrypted and then get uploaded to the aggregator. And the aggregator summarizes all the gradient ciphertext and applies the aggregation function on top of them. Now, as a fourth step, the client gets the aggregated gradients and they get decrypted via the homomorphic encryption private key. And then they may easily perform the model update. So as you can imagine, since we're talking also for federating machine learning, this takes place over multiple clients. Now, discussing a bit about differential privacy, the scope is to limit the information disclosure again. And how can we achieve that? Core context, kind of simplified, is that we add noise to the released model, and the noise is sufficient enough to mask the value of each party. So before sending its model, assume that we are adding some Gaussian noise. It can also be Laplacian, for example, to hide the exact, let's say, calculated value. And this mostly relies on the fact that most deep learning models, they're kind of resilient to minor changes. So the noise added should be quite small. Advantage is that it's fast to calculate while preserving high privacy standards. It's well suited for large data set, but the problem that it faces is that it could result to a slight decrease of the data model, of the produced model accuracy. So a differential privacy-based framework that in practice implements differential privacy is called PATE. So it stands for a private aggregation of teacher ensembles. Now, the work that's being performed by PATE is kind of non-compliant with the definition I just gave, and it works as follows. Suppose that you have a set of training data over here, the left side of the screen. This gets split and get passed to a number of teachers, and these teachers are the actual, let's say, federated learning nodes that perform the local training. Then all this information gets passed to the aggregate teacher, and the aggregate teacher then calculates a model. It's the basic model of PATE, but then this model gets passed to a student, and at the same time the student gets another round of training with an incomplete data set, different from the original one, but still relevant. And the outcome of the whole process is federated learning, federatedly trained, let's say, model being served by the students, but it's not exactly the same as the previous one. So the one holding the original sensitive data. Why is that? Because we have mixed the original prediction with another, let's say, public data set that even if it gets disclosed, we don't really matter. We're making a pause on that part. We're going to be back again later. And then now we're going to discuss a bit about how we may employ federated learning towards achieving active cybersecurity. First, a bit of introduction regarding what is a cybersecurity attack. Consider that you have a set of adversarial nodes or an attack group. What they usually do to compromise systems is that they attack it, particularly through networking. They try to search for vulnerable nodes in a network. They may enter there and then try to break the overlying, let's say, security system, firewalls, intrusion detections, and stuff like that. Of course, the original scope of the attack is to make the computational environment unsafe for operations. They can enter, take some data or alter data so that they can manipulate the system behavior. So what we argue here is that federated learning might be applied for the attack detection. Mostly, machine learning is used for signature-based techniques. So detect known attacks by using specific traffic characteristics, for example. This could be relevant to parsing logs from intrusion detection systems like Snort or Suricata, or private ones like FortiGate. And then there is also anomaly-based techniques that they take the original, let's say, flow of logs, and they model the normal behavior and try to detect when when the detected behavior is falling out of this scope. So it's considered abnormal. Two types of algorithms, as always in learning: unsupervised algorithms like autoencoders, and then we can also have supervised algorithms like ANN, random forest, of course SVM and SVR when we are talking about time series, and definitely K-means clustering, which is also suitable for splitting the data and having the updates at a later stage. So two main classes of algorithms, and then there is also a generative adversarial network part, which is kind of an unsupervised learning based on supervised feedback. So it's kind of a hybrid thing. And what we have seen in IoT Engine through all this work that we have been researching on, it's that CAN-based models, they may be successful candidates for implementing intrusion detection systems. And in general, they can be used for intrusion detection, malware detection, and to identify defense strategies against different attacks. I'm not going to talk about the last thing though. I may ask a question if there are some. So first of all, what is a generative adversarial network? Suppose that we have a training data set. We first have a discriminator being able to identify the normal behavior, let's say, or as we discussed before, what's normal. And it basically acts as a multi-class classifier. At the same time, there is a different network. So one network is the discriminator. There is a different network, the generator, who's acting as a different source of information. So it offers raw and labeled training data. So what's the deal? The generator generates data, feeds the discriminator. The discriminator responds with whether this is an attack or not. And based on the feedback of the discriminator, the generator is able to learn from that, train its model. So it takes this information from the discriminator as a labeled data set, and then produces a next round of data that could be, let's say, of interest to the discriminator. The idea behind that is that first it's the generator that learns, and then from the update of the attacks that get passed through the generator, it's the discriminator side that performs the learning. So the discriminator is used to train the generator, and the generator is used to train the discriminator. It's kind of interesting. And the idea in the end is that the generator learns so well how the discriminator works that in the end it is able to generate data that are considered normal. So the generator in a cybersecurity context, it could also be used to produce synthetic, for example, attack data based on the experience of training over real data sets, as we discussed before. Another interesting part is that using this approach, the generator is also able to generate data that are known to the discriminator in the first place. So we are able to offer exploration services, let's say, towards that direction. And last, they seem all this framework seems to be an ideal technique to train a neural network on an established attack and model similar, let's say, attacks. So in AIoT engine, we consider the discrimination as a component. We call this MAD, from malicious attack detector, and it's actually trained by exploiting network logs, model poisoning data sets and stuff. We have a set of data sets listed if anyone is interested. So when mixing everything together and with reference to the first slide that we have, the overall approach it's like that when applying PAIT. So we still have the same distributed, let's say, federated learning, the federation of learning nodes being employed, and then we have PAIT. So all the federated things here, they are the teachers, and they communicate the model to the federated learning server, which is then the student. So this is how PAIT may be applied in practice when considering differential privacy. And if we also consider MAD, as I described it before, the figure changes a bit like that. So we should have a MAD component, both at the edge part and at the aggregator node. The PAIT framework is exactly the same. However, in all cases, we have MAD kicking in so that it may also used to train and identify attacks against, for example, model poisoning or re-identification attacks. So as an overall, that was it. I think I have 45 seconds left for a question or two.
Thank you for being perfectly in time. There is a question in the chat, Artemis, or I don't know if Louis Muhammad would like to ask it, if you want to take it. And I've got also a very short question if you have.
Yeah, let me stop sharing so that I can actually check it.
There are two questions now in the chat. So the first one is if you provide some formal guarantees for security mechanisms. And the second question is in the PATE framework, where is the training up to the aggregator teacher taking place? Is it done in one entity or is it split and allocated to more? And I have also a third question, which is a simpler one, which is, that some of the challenge, I mean, you gave a very nice overview of all the cybersecurity challenges, but I guess a lot of them are not peculiar to federated machine learning or the edge, right? Things like
yes, exactly.
Are things that you're addressing anyway in machine learning. So what makes it special, for the edge?
Particularly for PATE and what we consider in IoT engine. As I showed before in the first slide that I had for federated learning, you may have the learning processes running over the edge, so aggregating data that come into the edge via channels implemented as digital twins. So we may gather all the information at the edge and perform the teacher learning at the edge. But it could also be the case that under a fog perspective, as was also discussed, the teacher learning takes also place on the IoT node if it is powerful enough. So it's entirely customized at the IoT engine part for the edge and for the fog.
Okay, any other comments on the formal guarantees? I don't know if you get this question.
No, I'm not sure I understand the question on that. So if they could speak up and explain a bit, then perhaps we could have a very, very short conversation.
Yeah, sure. So basically I was asking whether you provide any formal proofs for the security guarantees. The security is very critical, these primitives and all the stuff. So it is very easy to mess up the things. And then you provide, whenever you have a new solution, you provide the room for the attackers to catch you somewhere. So you
of course.
Formal proofs and formal methods where you guarantee that it actually works. So do you have some kind of proofs for your system?
As we speak now, PATE offers some guarantees. First of all, I would like to say that I totally understand your question, and it's actually pretty valid. Whenever you are employing a new system in another system, even to protect it, you may reduce a bit the attack vector on the original system, but still the new system has its own attack vector, so you may end up increasing that. So PATE, they offer some security guarantees for what concerns MAD and all this generative adversarial networking. It is on the context of the project to offer such guarantees, so we're going to perform tests, extensive ones, to offer the guarantees, but as we speak right now, this work is really primitive, and as we speak now, there is no proof. In 2 years' time, if we're having another relevant session, then I'm pretty sure that I would be able to offer you a set of guarantees or sets of tests that we have performed that have been either successful or unsuccessful.
Thank you, Artemis. I will ask you to stick around, for the discussion also in the end. Thank you.
Sure, I will be here.
And you making yourself available in the presentation. Let's go straight to Arne, boarding from Siemens.
Hello, everyone. This is Arne speaking.
The floor is yours, Arne. You can share your presentation.
Can you see me?
Yes.
And hear me? Great. Yeah. So I will do this presentation together with my colleague from the project, Sumuru. Are you also there?
Yes, Arne, I'm also here.
Great. Okay. Then I share my screen. Just a second.
We will see straight how we build stuff here, right? So I'm a bit more practical. Yes, let's see. Thank you.
Mm-hmm. Yeah, so it's a little bit more practical. So in general, our presentation is more about, let's say, use cases. for federated learning in IoT contexts or at the edge. And we do these use cases currently in our project Intelliet. So here you find also the project website with already some deliverables even presented there. So before I explain the use cases from our current project, I would like to look at a previous project that we dealt with. Also an EU project. Sumudu will explain some of his previous use cases. Yeah. So in this case here, us as Siemens brought in a use case which was about grease leakage detection in wind turbines. So you see here a wind park, and the common problem there is if you zoom into one of these hubs of a wind turbine, you see here now the inner part of the hub. You have these main bearings, so where the fixed part of the turbine comes together with the outer part, the rotating part. There you have sometimes, it's a rare event, but can happen that you have grease leaking out. So this is how it looks like. So over time can get really ugly. And you want to prevent that from happening, or you want to detect it early on. And we solved this in a project where we brought in the camera into an infrared camera, so that we don't have to leave the lights on here, into the wind turbine. It was basically located here, and then could take photos or a video stream of that of the bearing, and then we would analyze these pictures, and we trained this whole thing using federated learning. And this is basically the general concept which you've heard about already in the previous presentations. So also in our case here, we had local AI models locally in each of the turbines, and these agents would retrain the local AI model in case of an event such as the grease leakage, and would then send the model update to the server. So collecting and aggregating the AI models, which was simply one dedicated wind turbine in the wind park that would do this, and merge the models and federate them out to all the other participants again. Yeah, so that worked well, and that's basically also what we are bringing in now in our current project. So benefit for us here was mainly communication efficiency. So the wind park that we were dealing with was having a rather limited communication network, and since we didn't have to transmit all the training data but do the training locally, we were basically creating an efficient solution for them. Yeah, another benefit, as we have heard now, also is data privacy, as you know, which was not that relevant in this use case. Okay, so Sumru?
Yeah, thanks, Annie. So now I'll go through with like two use cases we have done. Mainly these are some research works. The first one we consider about ultra-reliable low latency communication in wireless networks. Here, vehicular pairs communicate over shared spectrum with the target reliability maintaining in terms of maintaining a low Q latency. So the baseline idea, all vehicles satisfy this target reliability, but of course there are some users that violate this maintaining this Q latency condition. So basically in the baseline settings, they neglect these users. So our idea is to model this Q length tail distribution and use that knowledge to control transmit power, and ensure those the users who violate this Q length condition, but still they manage to maintain a much lower Q length. So, but the main problem is when we want to model this tail distribution, vehicles has to share this Q length information with a central server, which require some additional signaling overhead in this this vehicle network. So our solution is to use federated learning. So each vehicular pair could estimate this tail model locally, and once a while they share this information with parameter server. So the whole network of these agents manage to learn these distribution parameters using the FI setting. If you click yes, so this problem we casted it as a network-wide power minimization problem under the constraint maintaining queue stability and reliability. So the reliability is the probability of maintaining queue length exceeding a certain queue threshold is maintained below a fraction of epsilon. So that is a baseline model. So, but in our case, what we did, those users that exceed that violate this condition with this epsilon fraction, we try to control their queue lengths and try to make sure those queue lengths does not exceed too much. So in this regard, we use extreme value theory to model its tail distribution, and we managed to find analytical model for this tail part using generalized Pareto distribution. Now the idea is to identify these parameters that define this Pareto distribution. Then we carried out this scenario in a simulated environment. If you go to next slide, we have a couple of results. Yes. So basically, we have this baseline model where the reliability is only the sole goal, and in our proposed cases, we consider about the users that does not meet this reliability condition and make sure they don't have extreme queuing latencies. So if you look at the first figure at top left, we can see almost all three managed to have maintain a low transmit power, but we notice that the baseline seems to be having much better performance in terms of minimizing transmit power. But when we move to the right side, when we compare the reliability, we could be able to see that it was in a price in terms of having a bit poor reliability. Now, when we compare the centralized and federated learning setting, if you go to the right-hand side down figure, there we can see both centralized and federated learning setting seems to be achieving quite similar performance in terms of reliability. But the advantage is in the amount of data that has been exchanged with the central server. So with federated learning setting, as we increase number of users in the system, we could be able to see the amount of information that need to be exchanged with the centralized entity is quite less compared to the quite less in federated scenario. Then the last figure we have checked about those epsilon fraction of users that violate this queue length condition. Since baseline doesn't have any control over them, we could be able to see their queue lengths start to grow quite a lot. But with proposed settings, we could be able to make sure those users manage to maintain somewhat reasonable queue lengths. Next, we move to another use case. Mm-hmm. So here, what we did, instead of using federated learning to improve communication aspects, what we did here, we consider about improving federated learning performance when there are limitations in terms of communication and computation. Now, in this scenario, we consider about a set of workers carry out federated learning tasks over wireless links. They have limited computation capabilities and they have limited wireless resources. So they have to make sure their federated learning accuracy is in a good level within a given number of communication rounds. So the baseline, either you schedule these workers randomly, or you spend some of these resources to estimate these channels, and based on these channels, then schedule some of these users over these channels. Now our idea is to identify who will be the computation-based strugglers and communication-based strugglers. So basically, we can avoid them while ensuring we can reduce the loss of accuracy. But the problem is how to predict these channel conditions, and then how we can ensure this loss of accuracy is minimized when we do this subset of clients are scheduled. Therefore, first what we did, we derived an analytical expression for the loss of accuracy when we do this subset of client scheduling. then we optimize it along with channel exploration and prediction. We cast it as a joint resource block allocation and client scheduling problem. Here, the objective is to minimize the trade-off between loss of accuracy and channel exploration. This loss is calculated compared to a centralized training. And for channel prediction, we use Gaussian process regression, which is a time series-based prediction method. Therein, we have a metric in terms of prediction uncertainty. We use it as a channel exploration metric. So the constraints are available limited resources and a set of predefined deadlines imposed of local computation and local model updates. Then in the simulated scenario, if you go to the next slide, we have these two baselines, random scheduling and proposed fair scheduling. In these proposed methods, what we did, we use our derived analytical expression to track the loss of accuracy and try to reuse, improve, optimize the client scheduling over it. But in there, we consider three cases. First one, these workers are aware about their data size compared to the total data distributed over the network, and they use channel estimation by spending some of wireless resources. The second one, workers are unaware about their data set size. Still, they use the channel estimation methods. And the third one, we adopt a channel prediction method on top of the client schedule. For the benchmark purpose, we have federated learning with no constraints on wireless conditions and computation resources. So for these resources, the scenario we have considered like 10 workers and different number of wireless resources. So if we look at the first figure at the left side top, therein the blue line, the dark blue line represents the benchmark, which result in the lowest loss. And in the top, we can see the baselines. They are quite far from this benchmark. And in between this green and red, they are corresponding to our proposed methods. But red is using some of wireless resources for channel estimation. So whereas in green, we do the channel prediction. So we have more resources for the client scheduling. Next, in the other figure, we have two scenarios comparing under different wireless resources. But I will move to the figure in the right side for more details, because we compare in that increase in number of resources. We compare what is the loss of accuracy by the end of the training process. We could be able to see that all methods, of course, manage to lower the losses with increasing number of because with increasing number of wireless resources, it reduced the number of communication struggles. In the bottom one, we changed the number of local SGDI iterations. So basically, we could be able to see that once we start to increase number of local SGDI iterations, yes, the loss of accuracy decreases. But after a certain point, it starts to increase. The reason is computation also has a certain deadline that has to be carried out within the local training has to be carried out within this deadline. So if once we start to keep increasing the local number of SGDI iterations, it started to introduce computational struggles that resulted in poor loss, so increased loss. Finally, in the left side bottom, we check how generalized this global model over these distributed users. We could be able to see that our proposed method is somewhat achieving the same behavior as the benchmark. So it generalizes well over different devices, whereas in the baseline, if you start to do the random scheduling without knowing how their scheduling affecting this federated learning accuracy, the models are not going to generalize well over different users. Okay, now I'll hand over back to Arne.
Okay, so now I would like to shed some light on the use case current project. Before I come to that, wanted to basically conclude here or have a preliminary conclusion of when federated learning actually makes sense. So, and for us, this was two main reasons here. So one, of course, is training is still reasonable for the AI model. Yeah, so you want to still improve the AI model. Improvements are in general possible, and maybe they are changing the AI model. Second, so reason for federated learning specifically now is that the data shouldn't be transferred. Yeah, so and that could have two sub reasons. One is network constraints. So you heard that already in the previous example of this wind park. Yeah, you have high amounts of training data. You don't want to send that around in the network, or you have high number of workers, and then simply this transferring gets big. So, and then the second reason is the privacy concerns, which you also face. Yeah, so the use cases in Intelliet are three. So the first one is agriculture, which is coordinated by AVL, an Austrian company, bringing in this tractor, which you see here at the lower right. And in this case, we want to develop an AI that allows the tractor to autonomously go over a field and do some tasks like harvesting, for example. Yeah, and besides this tractor, we have also an edge slash IoT infrastructure in place and a human operator, which could be, for example, the farmer himself, which is capable of interfering in case there's some reason for that. So. Our idea for this use case is now that this human operator, so for example, a farmer defines the goal, say harvest the field X. This goal gets translated into a proper, let's say, plan, and this plan gets deployed to the tractor, and the tractor does its autonomous operation based on AI, and then suddenly there is after perceiving the environment, an unknown obstacle turning up, and the AI is not capable in this case to handle this unknown obstacle, and then we assume that the tractor requests a takeover from this human operator. So you see here already there's an augmented reality glasses indicated here, so that's also a technology we want to employ here. So the human operator basically takes over remote control of the tractor and circumvents the obstacle. And from this interference of the human operator, we want to then update our AI model. Yeah, and that update, so this retraining of the AI, will then be shared to other tractors, so that they also gain from this further learning of the AI. So why federated learning in this case? Well, first of all, we have common objectives for these tractors. We do have also communication constraints, and we have limited data availability. So these events might be rare, and then it's beneficial for tractors to gain from this. The second use case is about healthcare, and here we want to do autonomous, let's say autonomous advising of heart patients, and we are working here together with our partner Pagni in Greece, which is a hospital, and they will provide basically the patients and clinicians overseeing this. And as the IoT device, we will use a personal device of the patient, plus wearable devices carried by the patient that will provide data, feeding our AI, and the AI will basically do some health data analysis upon that data, and will then conclude with health recommendations for the patient. And in case there's a serious event, there will be an escalation also to the clinicians, which then direct the patient further in what to do. Yeah. Apart from directing those recommendations to the patient, also the personal device will get some, will be receiving this advice in a structured way, and we can again retrain our AI model based on this input. And here again, we want to then report about these model updates that we basically determine locally. So this will be on the one hand to the hospital where such an aggregation takes place, but we are also considering doing cross-patient model federation, so in a peer-to-peer kind of fashion, or via the hospital. So that needs to be determined. Then once we have that aggregated at the hospital, we think even further to also cross-site model federation. So essentially exchanging this and sharing model updates with other hospitals. Why does federated learning make sense here? Well, we have these privacy concerns from where we can benefit with federated learning, which has some sort of privacy by design. We do have also communication constraints with IoT devices, and also somewhat limited data availability where we can benefit from federated learning. Finally, we have the manufacturing use case. This is led by Siemens, so us, and here we have a robot arm in a, we assume a manufacturing plant which can receive all kinds of manufacturing jobs. So it's kind of a generic manufacturing plant, and this robot arm can interact with different machines. And in this case here now we have a customer that defines this, again, a goal. So for example, this could be, please construct a chair for me with these and these properties that is received by our infrastructure, so the edge infrastructure of the plant, where we calculate the processes or compute the processes and machine orchestrations, and accordingly task the robot and the machinery to work together. The robot has an AI to do this autonomous operation, autonomous interaction with the machine. So specifically workpiece handling we want to focus on. So assume, for example, wood pieces that should be engraved or should be cut by engraver or a CNC machine. And the robot has a task to put this workpiece correctly into the machine. And there might be workpieces wooden workpieces which have a shape that is basically new to the AI, and then again we have the scenario that the human is asked to basically guide the robot, and then the AI, so the human gives this input, and we can again learn and do a retraining of the AI based on this human input. So in this case here, you also have augmented reality included here. Again, you see this indicated here with this image. So we have a stylus and augmented reality glasses that allow us then to guide the robot arm in the correct way to place the workpiece. So this retraining will result in a model update that we again communicate. It gets aggregated here at the central point and then shared with other, or federated, I should say, to other robot arms as well. Right. So why federated learning in this case? Well, similar to the other cases, we have again common objectives in similar machines. We have, it might be that we have limited connectivity in such plants also, and there's also a privacy concern if you consider now that this plant receives construction goals from maybe even competing companies, then it makes a lot of sense to also be very protective of the privacy for these customers. Okay, that's it from our side. So if you have any questions, please let us know now or later in that comment session. And also we invite you to check out our project website here.
Thank you very much, Aaron. There has been some discussion on scalability in the chat. I don't know if you want to make any comment or your colleague. Otherwise, I think we can have 5 minutes break, and then Jens can prepare his presentation on the hardware part, and as he's preparing, we can have a 5 minutes break. I don't know if you or Sumuru or you want to have a say on the scalability discussion on the chat.
Yeah, actually, yeah, Sumuru here. So yeah, of course, I agree that because we didn't use any real simulators, because in our research team we just develop our own set of simulations to validate our theories, because our main focus is about finding theoretical aspects. But for validation, we use different type of possible applications. Yes, in that case, yes, we agree that in a vehicular scenario, considering 200 vehicles, 100 pairs, might be not reflecting the exact dense scenario. But the key idea is how well we can integrate this extreme value theory with federated learning to help to characterize this queue distribution that help us to improve the ultra reliable low latency aspects in the communication. So of course, with the more computation power, more resources, we could validate for much larger scale networks. That is somewhat like a part of our goal of joining this EU project, where we can access to the real data and real scenarios, so we can validate these theoretical algorithms we have been proposed, whether they work really well in the real scenarios, rather than simulating and making claims. But of course, theoretically we can achieve those parts, but we can now, our target of within this project is to see how well they work in the real applications.
Okay, thank you, Sumuru. So I suggest that Jens prepares his presentation, and we have 5 minutes break. So we are back in at 10:55, right, to start with the final session. Thank you very much. The deep learning, Jens, and maybe we can start the recording again.
The recording is recommenced.
Very good.
Okay, so welcome everyone from my side. I guess you can hear me and see my screen.
Yes.
Okay, so again, welcome. So I'm Jens, together with Carola. We are the coordinator of Vetliot. This presentation will be a little bit different from the others, as we are focusing just on the accelerator part of Vetliot. That's why we call this presentation Accelerated Deep Learning for Cognitive Edge Computing. Vetliot is short for Very Efficient Deep Learning for IoT. You can, on a high level, divide this into 3 parts, which is the platform, which I'm focusing on today, the use cases, which I will also briefly introduce, as well as the open call, which contributes to the use cases that will start at project midterm. Vetliot, just to give a short introduction, consists of 12 partners, which are spread all across Europe, so from Portugal to Sweden in the north. This is a high-level overview of Vetliot. So it's have the cognitive, what we call cognitive IoT platform here at the bottom, that I will tell more about in a minute. Together with the accelerators, this is then the foundation for really the Vetliot toolchain, which is an optimizing toolchain, really then allowing to really map the different use cases that we have in the project. So we have one from automotive, industrial IoT, as well as smart home, together with the open calls, then mapping those really towards the different accelerators and the hardware platform. This is then also covered by the requirements engineering in the project, especially important for the, for example, automotive use case. together with the security, robustness, and safety aspects, which are really important if you want to run your IoT applications in these critical use cases, but which will not be part of today's presentation. So what the goals that we have in Vetliot are, on the one hand, to really have a reconfigurable, heterogeneous, and scalable IoT platform. We are targeting at a 10x performance improvement for the accelerator part, which will then also translate into respective energy efficiency improvements. And using the toolchain, we are also looking at an efficiency improvement, not only in terms of performance or energy efficiency, but also in terms of productivity, for example, as this toolchain then allows you to map your use case quicker to the and in a more optimal way to the hardware. With respect to the hardware platform, what you're typically facing in not just IoT, but also, let's say, cloud applications, is that you have a, let's say, zoo of different compute platforms, like, for example, FPGAs, CPUs, traditional ones, or ARM-based ones. We have RISC-V, which is also a big part of Vetliot, as well as other specialized machine learning ASICs, for example. And you then need to map really on the one hand to your use case, and on the other hand also then need to deploy. So this is something which Vetliot addresses. So we are providing a heterogeneous modular scalable microservice system, which is covering, let's say, the whole range from cloud computing to embedded computing, also covering then the IoT and edge computing aspects. I guess fog was also mentioned previously in one of the presentation. We are doing this, as you can see here, then via different base systems, or what we call RECs, for resource efficient computing and storage. This is a term or a product term which is introduced by one of our project partners. So all the way from really cloud via edge to embedded computing. And as you can see, the nice thing about this is that we can then, for all these systems, have those heterogeneous compute devices populated in these systems. So this then, let's say, gives you the opportunity to not just improve performance, but also improve maintainability, reliability, and energy efficiency, and so on. I will now shortly introduce those different systems. On the one hand, we have the Rex box system. This is the very big one here, focusing more towards the cloud part, or very, let's say, big edge applications. The whole system consists of a number of carriers. You can have either the high performance ones, which, so as said, we call those microservers, and that allows us to integrate, let's say, high performance microservers either based on CPU, based on FPGAs, or different technologies. As said, it's a heterogeneous modular system combined with what we call low power microservers. And those are then, this is the nice thing about it, coupled to a different set of communication infrastructures. One is the compute network, management network, as well as a dedicated high-speed, low-latency communication network that is quite important for quite a range of applications, as let's say, low latency, especially for let's say the more compute-intensive scenarios, is quite critical. So this is, let's say, the big-end systems, and this, there are also, let's say, scaled-down systems available. For example, what we call T-Rex. That's a platform optimized more for the edge use case. It consists of just 3 microservers. You can basically populate the same ones. Those are based on existing computer on module form factors like you might know ComExpress, ComHPC, SMARC, and so on. And also here we have a particular emphasis on the one hand management, so you can monitor and manage your system. You can yeah, for example, do all the different characterizations that you might need. You can have remote access to the system as well. And yeah, here we are really integrating all the different interfaces that you require for your edge compute use case. And then this is even further scaled down. This is something which is currently under development. We call it microREX, which is focusing more really on the embedded side. So we have even smaller computer on module form factors integrated like SMARC or Jetson NX, which I guess it was Jetson Nano, which was also mentioned in one of the previous talks today. And all this is then coupled to, on the one hand, communication interfaces, wired as well as wireless. We have a particular LoRa emphasis in Vetliot, as well as 5G, and the different accelerator parts, for example, this M2 accelerator, as well as the different sensor and actor interfaces. With respect to what is really then used for the computer, as said, it's a modular system. So we are covering quite a huge range of microservers, again divided into the CPU, FPGA, GPU, and specialized machine learning accelerator parts here, covering, as you can see, the whole spectrum. Parts of it has been mentioned already today. As said here, the Jetson Nano. I guess there was also the Intermovideos, which I have not here on this slide, but also the, let's say, more high performance ones like, for example, here are 32 core Cortex A72 on the CPU side, or Intel Agilex or Stratix 10 FPGA that we can populate in the system. So this is, let's say, then the modular hardware part. What we have then also is, let's say, the FPGA part, which has a particular emphasis in Vetliot. As you all know, so on the one hand, we have those heterogeneous accelerator part here, which is basically then used by the Vetliot toolchain to map your particular use case to the, let's say, the optimal one. So which is typically then a combination of either GPU, FPGA, or specialized ML SoC. So this is, let's say, one part. The other part is then really have approaches in a co-design fashion. So using then FPGA, specialized FPGA accelerators for your particular use case, which are developed in a what we call architecture way. So optimizing not just the hardware or the model, but really optimizing both ways or both sides of this thing, so that you can then for example, adjust the precision that you have in your hardware towards the model, adjust the topologies, also adjust the way the things communicate, and on the algorithm side, then doing the same. So this is what is then really done in a, let's say, co-designed fashion. This is a quick overview about the tool chain. We have with a small SME, a startup in the project, which is especially focusing on the optimization part here of the deep learning models. So really combining different models and then mapping them to those different hardware substrates. And then, let's say, quickly introducing the use cases that we have in Vetliot. On the one hand, as said, that's smart home. So the idea that we have there is to have a centralized interface for the user of such a smart home. This is a smart mirror, which will then act as a central user interface towards the smart home, controlling different actors like the kitchen, like the wardrobe, and so on. And also, for example, offering personalized information like the public transportation schedule, like the weather, football scoring things, and things like that, to keep all this private. As this has been mentioned quite a couple of times already, we are not streaming everything to the cloud, but doing computation locally, so that things like face recognition, object recognition, gesture recognition, and speech recognition is really not processed in the cloud, but locally on the device, or at least within the smart home. Another use case is the industrial IoT use case, which is covered by Siemens. So Siemens is also part of Vedliot, not just Intelliet. So there we have these, on the one hand, the drive condition classification use case. The idea there is really to attach a small IoT device to such a drive here, and then without measuring the actual device current, just without measuring, let's say, other parameters, do a condition classification as well as arc detection for DC distribution systems. So this is really, let's say, what is typically called industrial IoT. Another use case that we have in the project as well is the automotive use case, which has been brought into the project by Veoneer. So there we are looking a lot at really distributed computing, so doing all the AI processing in the car as well as at the edge, and looking at all the different reliability, security, safety aspects which are popping up in that use case. So that's all from my side. I hope I was able to save some time here. As said, this project, as I guess all the other ones as well, has just started, so be part of it and be also part of the open calls, which are going to happen early next year. Thanks a lot. Any questions so far?
Thank you, Jens. Well, I see some questions in the chat, but I guess, Marcin, this concerns the previous talk, right? Can you clarify? Yes, I guess it concerns the previous.
I think so, yeah.
Not.
Yeah, we continue our little discussion with Sumudu, so this is, probably we should switch to a different channel. Sorry.
No problem. Well, I think that this thing you raise is, I guess, a wider problem, right? I mean, even the autonomous driving in California, right, is not tested in the scalable conditions, right, that you expect a car to be. But Jens, I have just a question, right, which is, on the certification of these devices, right? Because earlier we've seen also, the security stuff. We know that there are also, the new EU regulations about human oversight testing and so on. So I was wondering what happens with the certification of the hardware, right? Especially if you want to use it, in applications like automotive, things that can be not just a financial loss, but they can have life-threatening implications. So yes, how does the certification process work for the hardware devices in general and in your case?
So within the project, we are also looking into things like functional safety. If that is your question, if you are really looking, let's say, at the hardware level, there you have let's say, particular redundancy schemes and so on and so forth. But let's say functional safety is more than just the hardware. But you also need to, let's say, push this through to, let's say, all the, let's say, software and learning levels. And this is something that we are just starting to work on in Vedliot as part of the requirements aspects.
So, I guess also every industry might have their own requirements, right? For example, in healthcare, we've got the CE marks, right?
Yeah. So this is different.
So it depends also on the industry, right?
It depends on the industry. As said, in Vedliot, this is mainly driven by the automotive use case. Typically when you as you say, when you develop something for autonomous driving, this is, it needs to match all these functional safety requirements, which are typically there in automotive. And this is not that easy, in particular when it comes to machine learning, as you know. So on the hardware side, I would say it can be addressed with let's say the typical redundancy schemes that you have in place, and all the qualifications that you do for temperature, vibration, and so on. That's I guess doing, but it is really more interesting when you look at it from a functional safety point of view, including the software part, including the aspects that you connected through a wireless network to parts of your processing devices, things like that.
Do you have an OEM for automotive in your consortium, or?
Yeah, exactly. So there's Veoneer, as said, they are dealing with those things. Okay.
So thank you very much for saving also, a couple of minutes for the presentation. Yeah, and I think we can move to Jussi to share his presentation. Actually, when I was looking at the registrations for this seminar, I saw some people, from ports joining, actually a lot of people, something like 10 or 15 people, at least in the registration. I don't know if they are here. And then, looking at the title of your presentation, I got the reason. So we'll hear federated learning in maritime, right? So, there were some, 15 or so people joining from the maritime industry and from ports. So the floor is yours. Jussi, feel free to share your presentation, introduce yourself.
Thank you, John.
The presentation.
I hope you can hear me and see the presentation okay?
Yes.
Yes, we see it very well.
I'm very happy to hear that we have people from the maritime side also attending. My name is Jussi Poikonen. I'm representing the Ingenious project here and discussing applications of machine learning and edge computing, especially in maritime logistics. And the idea is to focus on a pretty high level on the applications and some flavor of the kind of methods that are used in those, but not to go so much into the technical details. So this is a little bit more high level, I think, than any of the other previous presentations. So very simple overview. First, I'd like to introduce myself and the Ingenious project briefly. And then the main part is to discuss these applications and what are the related use cases and implementations in the Ingenious project. And perhaps if we have time, I would like to discuss a specific use case which we at Awake AI are working on in the Ingenious project on predictive port traffic analytics. But yes, briefly on our background, I'm one of the co-founders of Awake AI, and all of the co-founders and core development team at Awake have a background at Rolls-Royce Marine, developing autonomous and remote controlled vessels. This image shows this kind of sensor fusion data from the world's first fully autonomous and remote controlled road ferry. At Awake, we focus more on port digitalization, providing situational awareness, communication solutions, optimization solutions, and for example, predictive analytics for ports, which is what led us to the Ingenious project. So if we jump right into that, is short for next generation IoT solutions for the universal supply chain. Now, Ingenious focuses on quite a lot of different technological solutions that are applicable in various parts of this kind of multimodal supply chain, of course, including the port as a kind of central component or area. So we have work related to sensor implementation, IoT, communication networks, data layers, and then kind of data processing like data virtualization and distributed ledger technologies. Also cloud machine learning technologies on a very kind of broad range of technologies. And these are applied in different parts of the logistic chain. For example, looking at automated machinery in ports and factories, looking at tracking cargo and vehicles in the transport, then this kind of generic data management issues, and of course the kind of holistic view of events in the logistic chain and providing predictive analytics for that. So next, I'd like to kind of focus on a few of these examples. So I've tried to gather here these kind of broad areas where edge and machine learning are relevant in the maritime logistic chain. And these are kind of organized in the order vertically of increased or kind of a lot of focus on edge processing and these kind of autonomous elements doing processing and machine learning and that kind of things, towards more cloud focused things where you need to collect distributed in the cloud. So this is of course not so strict in reality, but I think that this is a kind of a some kind of mental map of how these these kind of areas what kind of technologies they require. And I also tried to gather examples in the different parts of the maritime logistic chain, which is of course centered in the port, but involves critically sea transports and also somewhat the hinterland traffic side. So the topics that I wanted to discuss are, first of all, autonomous and remote controlled vehicles. On the sea side, autonomous vessels are nowadays called maritime autonomous surface ships, which is of course very dear to me due to our background. In the ports, maybe a more relevant technology is these AGVs, automated guided vehicles. And of course, in the hinterland and road traffic overall, there are autonomous cars and especially autonomous trucks. Another area is this kind of IoT based monitoring of events in the logistic chain, situational awareness, and perhaps more generally this kind of digital twinning, meaning that you have a simulation of what is happening in different parts of the logistic chain, which is synchronized to real world events. So of course this relies on having a lot of different sensors which are able to provide you with real-time information on everything. Like, for example, in the port case, starting from bollards, you know, what is the pressure coming into a given bollard on a given pier? On that level, you know, for example, ports would like to have this kind of digital twin information. But some examples generally on this kind of monitoring include, of course, vessel tracking, container tracking, smart fairways. So, for example, sensing the conditions of fairways and vessels moving there, representing that digitally. In ports, cargo tracking is of course important, and generic monitoring of the contents of, for example, storage areas in the port, and kind of overall digital twin development of the ports. And on the hinterland side, very kind of a widely used monitoring solution is this automatic gate systems and vehicle tracking overall. Then I'd like to talk a little bit about predictive asset management. This mainly refers to predictive engine health and energy management, and overall kind of machinery health management used, for example, with cranes in ports. So predictive engine health management aims to kind of make the maintenance cycles of vehicles longer, whereas energy management is used quite a lot with, for example, electric vehicles, where it's very important to make sure that you are kind of aware of how much energy the vehicle is using to get to point B from point A. And then finally, where especially our organization is focusing most is this kind of scheduling applications and optimization. So, for example, predicting various events in different parts of the logistic chain, like times of arrival for vessels and trucks, providing this kind of just-in-time arrival information to make for example, sea traffic more efficient. I mean, it is more efficient for a ship to arrive just in time than to come full speed and wait near the port due to energy consumption reasons. And of course, in the port, there are applications like cargo operations prediction. So trying to predict, say, for a given vessel, how long its discharge and loading operations will take to enable better planning of operations in general. Now I'd like to talk about some specific examples about these topics, both generally and also with regards to the Ingenious project. So we start with this autonomous and remote control vehicles. A very typical application of machine learning in that field is object detection, classification, sensor fusion, and generally this kind of providing situational awareness of what is happening around the vehicles. And if we look at this kind of a high-level diagram of the systems in autonomous vessels, you can, well, it is here divided into the, first of all, the onboard system on the vessel and this kind of data flow from the sensors to kind of more abstract information. Then we have the communication channel, which is correspondingly kind of going from high bandwidth requirements to low bandwidth requirements, and functionalities in remote systems like remote control of the vessel, and of course going to the right, this whole kind of development cycle of updating, for example, machine learning models on board the vessel. Now, the kind of important characteristic of autonomous vessels is that the communication channel quality varies quite a lot. So that you cannot guarantee to have like 4G or 5G level connectivity in all cases, because the vessels go out at sea and really you cannot rely on that. So it is very important to have the possibility of this kind of almost fully autonomous operation in the vessels. And that's of course very challenging for the machine learning edge processing side of these systems. So if you want to remote control this kind of vessel based on camera data only, then that's really not generally guaranteed. But in the Ingenious project, we focus especially on these kind of cases where there is a lot of focus also on the communication solutions. So implementing these IoT 5G network solutions and integrating that with these remote control solutions. So one Ingenious use case is to apply MR, mixed reality solutions with haptic devices and tactile internet solutions to remotely monitor and assist these kind of automated guided vehicles in ports or for example, in factory areas. And there the objective is to implement this kind of immersive remote indoor cockpit, which is wirelessly connected through IoT 5G radio access network to the AGVs to be controlled. And of course, this requires very low latency and high bandwidth, this kind of typical tactile IoT characteristics, good sensor and edge processing design to make sure that the data quality is good enough for remote control. And of course, the kind of physical implementation of the remote cockpits and haptic solutions and so on. But this is more focused on the kind of edge and communication cases, not so much on the machine learning aspects. Then if we go to this generic monitoring and situational awareness, digital twin, there are many solutions which use computer vision, for example, character recognition or generic object detection and classification to kind of form this kind of views of the world, and also IoT sensing solutions, kind of custom designed for many kinds of tracking applications. Now, these examples are not really part of the Ingenious project, but this is something that we have been developing. So in ports, it's, as I said, it's very common to use this kind of gate automation, which uses computer vision to detect incoming cars and read their ID numbers, and also same thing for containers. Cranes can read the containers' ID numbers and kind of automatically detect these events. But also this modern camera and let's say deep learning technologies enable this kind of large scale computer vision also be used to, for example, analyze storage area contents. So this left example is an application where we look at this kind of a car import lot in a port and automatically detect where cars have left, where new cars have entered, and what is the overall capacity and situation in this area. And this is something that is quite interesting in many ports, for example. And here's another example where we look at this kind of generic, more three-dimensional storage area where we have containers which are stacked, and that's a difficult case for purely camera-based computer vision. So we have used LiDAR solutions to count and automatically inventory the storage area contents. So this is like a top-down view of this one generic storage area. And you can have this kind of over time view of say how many containers of a given type are in the area. Now briefly an example of this kind of monitoring solution work in Ingenious. There is one use case which focuses on tracking containers. So one problem in the maritime logistics is that there is no common solution, or kind of widely used solution for tracking containers and their, let's say, environmental conditions during, for example, sea transport and over the whole multimodal transport chain. So the objective of this demonstration is to provide this kind of end-to-end asset tracking using IoT sensors and satellite and cellular networks. This doesn't also involve really machine learning components as itself, but this kind of collected data can be used in another use case in Ingenious, which I will talk very soon about on situational awareness for port operations. So it's very useful if we can track the movements and what happens with a container as it comes from the vessel to the port and to the hinterland side. All right, predictive asset management typically uses, for example, unsupervised learning techniques, because if you are predicting the breakdown of engines and you are looking at, for example, ships engines that are very expensive, you cannot break down thousands of these to do good supervised learning. So I think it's very typical for this kind of applications to collect in a distributed way a lot of data from, for example, ships and trucks and kind of in a centralized way use unsupervised learning to do this kind of predictive asset management, classifying whether an engine is likely to break, for example, in the next month or not. And of course, this requires a lot of this kind of distributed IoT sensing solutions. Now, in the Ingenious project, there is one use case focusing on this kind of health management. So the idea is to implement this kind of economically feasible rail health monitoring, early detection of defects in wheels and bearings. the objective is to extend the maintenance cycles of these freight train cars in a power and cost optimized way using edge processing and efficient connectivity. And here's also a machine learning component. So this kind of a context-based data clustering is used at the edge using very power efficient neuromorphic networks. So the idea is that those will detect which data are actually something that is novel, would be kind of useful learning for these models instead of blindly transmitting all sensor data all the time. So it's kind of this preliminary novelty detection of the data, which is then passed to this kind of cloud learning models. Now, finally, we have this scheduling and optimization area where typically this kind of distributed modeling is done, supervised regression models, time series models, and optimization algorithms. So trying to predict the durations of process steps and trying to optimize planning according to the predictions. And in Ingenious, especially, we are focusing on this kind of use case where we integrate data from different sources in the port and the surrounding supply chain to model these interdependencies between the sea traffic and the hinterland traffic. Here, the main objective is to estimate future truck turnaround times and especially congestion in the port area. And this is focusing on Port of Valencia and Port of Livorno. So this starts from predicting vessel schedules, then based on the vessel schedules and information on their cargo, discharge and load estimates, we need to estimate somehow the cargo flow rates, and this is related to the truck traffic levels in the port. And finally, we want to identify the turnaround times and congestion in a predictive way. Now, I would have liked to a little bit focus on this use case, but I think I have used already too much time, so I can certainly discuss this in more detail with someone who is interested. You can contact me using the contact information at the end of this presentation. But basically, we have started on this vessel schedule prediction, and that is in very kind of good shape. We can do it globally, and next we will focus on integrating this cargo traffic data and trying to model the effects of vessel traffic on the landside congestion. All right, thank you. I think I have used all of my time.
Thank you, Jussi. There was no reason, to hurry so much, but thank you, yes, for trying to keep the time. So I was just checking the chat. I don't know if there is any question for Jussi from the port people that I guess, they were not just registered, but they joined as well. I saw some questions, but I think these concern the previous session is about the power efficiency of the hardware solution. So I advise people to see the chat as we are moving to the end of the workshop. And also there was some question for collaborations and so on. Well, I think that what I would say is that good for all participants to follow the speakers, to follow the projects on LinkedIn. Also our project EU-IoT, and maybe subscribe to our newsletter, because there are going to be a lot of funding and collaboration opportunities in the open calls of these projects. So yes, I mean, if you have a tangible interest of building something, and if you are affiliated with a company in Europe, there's going to be a lot of opportunity. So I don't know, Jussi, if you see the chat, there is a question from Mauricio. You might want to take it, and then I can move to the final presentation from my side.
Okay, thank you.
It's about neuromorphic networks. Can you see the chat, Jussi?
Yes, I can see. Okay, so yeah, I can answer here. Neuromorphic networks. All right, yes. I have to admit I don't have the kind of specific details about these neuromorphic networks, but if you would like to, for example, contact me, I can connect you to the research team that is focusing especially on this side in this health management.
Okay, I don't know, Mauricio. Yes, okay, thank you for this question being answered. So I'll go straight sharing. My presentation, I think it's connected to what was discussed so far, but again, it's kind of a little bit different presentation, but still on the topic. So I'd like to talk, I am from EU-IoT, as we said in the introduction. It's a coordination action. So we are not doing, research in this project like the other projects. But on the other hand, we are setting, agendas in collaboration with European Commission and the other IoT projects. And I would like to push also a little bit on the topic of IoT at the far edge, and more specifically, TinyML. So, what is TinyML, right? It is actually an alternative form of machine learning, or if you want, AI, at the far edge of the network. So we don't just talk about running machine learning on an edge or a fog device, which is something we have been discussing so far, but actually on a microcontroller, or in an embedded on a low CPU constraint and memory constraint embedded device. So that's embedded machine learning, but we can go to at the microcontroller level, and it turns out that you can run a machine learning model, even a deep neural network, because it's the nature, of performing calculations on the matrices. So it turns out that you don't need, an expensive hardware infrastructure to do this, but you can do this on a microcontroller. Now, if you do this, when you run AI on a microcontroller, you push some of the benefits that we discussed so far at their limits. So you've got, maybe you've seen the discussion in the chat previously. So you push the power efficiency at its limits, because what it really consumes energy, even at the hardware level, is when you do I/O, for example, right? Input-output operations. This is the most energy consuming, right, part of the embedded systems, right? And also latency. You are much faster and much more real time if you can detect insights directly on the microcontroller. And it's also much more green friendly, right? Rather than running AI on the cloud. And then you don't really need, continuous connectivity, right? So one of the applications, I'm not discussing applications here, but one of the applications is, for example, precision farming. So in large rural areas, you cannot take it for granted that you are going to have, for example, connectivity like LoRa or other type of LP, low power wireless connectivity to monitor, for example, cattle, right? So by putting a deep neural network and running neural network inside the microcontroller, inside an animal, you can get insights about the status of cattle, even without having to have continuous connectivity. So you get all the benefits of edge computing, but you actually push them at their limits. So now I'd like to become a little bit more practical. By just putting this at the overall landscape, right? So there was some discussion about cloud and edge and far edge. Of course, as I said, there is no silver bullet here. There is not a model which is the best for every application. So yeah, if your concern is to have many data points availability, you might be considering a cloud option. Whereas you go to the edge to have more faster and energy efficiency processing and better privacy preservation and real-time operation. And if you go to the far edge, then you get these benefits at its limits. So if we see that, for example, at the case of an industry use case that we have been deploying in past projects, like quality management or predictive maintenance, asset management in manufacturing. So there is indeed some good benefit in having a lot of data points and performing a remaining useful life calculation in the cloud, because this is more credible. However, it is faster to detect an anomaly and to be able to take actions to remedy a potential defect if the deployment is on an edge device for data collection, or even if you deploy this on a chip inside the machinery. So again, depending on what you want to achieve, you may consider a deployment which is at the cloud or cloud edge, or a TinyML deployment. And yes, today there are many boards. I'm just listing 3 examples here. Again, it's not a matter of advertising any vendor. There are more vendors nowadays that they are offering TinyML capabilities, and also toolkits where you can build machine learning for their chips. I don't know, Infineon is an example of a European vendor that I don't list here, right? But yes, there is the Arduino Nano 33BL Sense board, and there is good tooling with the Arduino IDE, and of course with data science workbenches like Python, TensorFlow, Lite, and Keras that allows you to build a deep neural network and run it on the microcontroller. Other examples are the SparkFun Apollo board, or from ST Microelectronics, the Disco Discovery board. Now, how does this work? Okay, on the one hand, it is data science, right? We use the same tools or the same toolboxes that we use to build machine learning pipelines. But at the end of the day, you will need also some embedded systems development expertise. And this is, what makes a little bit the development challenging, because as we know, it's rare to find in a single person skills, both in embedded systems, which are already very rare and challenging skills, and on the other hand, data science, machine learning, and AI skills. So this is a framework for TinyML, so you can use standard like Jupyter notebooks and Python and APIs from machine learning frameworks like TensorFlow and Keras for deep learning. But based on a special edition of TensorFlow, TensorFlow Lite and TensorFlow Micro, you can shrink the size of the model you build with a conventional Python pipeline and Python tooling, and deploy it on a microcontroller. Let's see, I've tried to put some steps if you want to get started. So yes, primarily you would need some data set to start with, or to simulate a data set, and you can find some open source data sets. Of course, data set for TinyML is a bit challenging, typically because we don't have, data sets that we collected on the TinyML setting, but you could start with other data sets for building a small toy application, and then you can go to your Jupyter notebook, of course, do this explorative data analysis, do the data split, and build a TensorFlow model deep learning model with Keras. Then you've got, of course, to make sure that the model looks right. So you've got to improve it. Maybe, you know, for the sake of accuracy, add some more layers in the deep neural in your deep neural network. You know, do some model evaluation, avoid the overfitting and underfitting, which can be likely here, or maybe, you know, even test different deep learning models. And then comes the embedded systems part. So in TensorFlow Lite, you will find two libraries, right? Two tools, if you want to call them this way. So the TensorFlow Lite converter, and this will help you convert the model into a space-efficient format that you can deploy in a CPU and memory constrained device, or even a microcontroller if you use the TensorFlow micro version, and then you know, an interpreter module, an interpreter tool that will convert this to the C program, right? It will convert the Python program to the C program that you can actually deploy and use on your microcontroller, like an Arduino sketch. Then once you've got the C++ sketch, you can, of course, typically the best thing to do is that you can test it, you can run it or on a conventional machine, and then you can use tools that are quite popular in the embedded systems community, like Arduino IDE, to deploy the binary on the microcontroller, like the Arduino Nano 33 I was talking before. Now, a nice thing is that this community is growing, so you will find a lot of TinyML startups that, you know, managed to raise funding and do interesting things in 2020. A very interesting mention is the Edge Impulse company, because they give you tools that you can address the entire pipeline. So you can imagine like AutoML tools, automatic machine learning for embedded machine learning development for TinyML, right? And they can even, you know, hide some of these steps or make them easier through shortcuts as soon as you use some of the boards that are already supported in the Edge Impulse ecosystem, right? So you've got a visual tool that you can build a TinyML pipeline for one of those boards, or even if you don't have you know, hardware like this, you can start and experiment and build something in your Android or iOS phone. Now, of course, these are, you know, just scratching the surface, because it's about, you know, building some machine learning for a microcontroller. Still, of course, you can build some interesting applications. Imagine, I don't know, disease detection on a plant, or the cattle thing I was talking before, or even in the predictive maintenance, in the asset management. That's where you can have real-time insights on a potential defect detection and get faster action. But imagine that it can become more challenging if you put it in the context of some of the presentations we've seen previously, right? So like, you know, having heterogeneous devices when you want to optimize their TinyML deployments, or even federating them, right, to learn a more accurate model, right? So, and if you add the mobility aspect, so federated learning in mobile edge networks with TinyML support, again, you can have starting challenges in terms of sharing model updates, taking into account the peculiarities of the hardware. I think some of these we've shared before. So I would like to end up, you know, by giving some resources. I think you can delve into more insights and build an example of your own. It's fairly easy if you follow some good resources. As I said, you can find a wealth of TinyML resources in a Gimpal's ecosystem. There is a TinyML book by Google people. You can find it in the tinymlbook.com from O'Reilly, and this is a good resource. And I think during the last 2 months there was the first, also Coursera course, which is an introduction to embedded machine learning. It's not a big course, like something like 3 or 4 hours with practical examples hands-on. By the way, in EU-IoT, we will be releasing for all the community a catalog, a searchable catalog of IoT training courses that will help you, find the course on the IoT training topics you need. And of course, we will continue in future seminars to create valuable training content with some excellent speakers like the ones we have today, maybe, on more edge or niche topics, because, although, I mean, we've researched, a list of more than 200 courses, you won't find, the content that we shared with you today in any of the existing, courses, right? Simply because they are dealing with more basic stuff of IoT development and deployment, right? So that's the purpose of having recording and making available these seminars. So I was not viewing the chat. I don't know if there are any questions or if we can proceed with the final questions. Overall, I think to all the speakers and the wrap up to the workshop. So let me see the chat. Yeah, I think that maybe Maurizio is right in the chat. There are a lot of TinyML courses emerging. I think the Coursera example was one. I think also in the edX community, and maybe that's the also where the Harvard class, I believe, is. If I'm not, and so on. So, and there is another question from Stefanos. Well, the pros and cons, right? Remember what I said in the beginning, right? It's not, and I think that's a good conclusion of all the edge computing stuff. There is not a single thing you have to do and a single device that you have to deploy, right? So I think what I would do, Stefanos, is I would take my business requirements and I would benchmark for what I want to do, right? So for example, what is the cost of the board, right? The cost of the board can be, and the cost of the hardware can be a consideration, especially if you have to deploy in many units, right? Tooling and communities and ease of development is another thing, right? So I mentioned, Arduino. You can imagine that Arduino has a community of tens of thousands, right? Probably hundreds of thousands of developers, right? So depending on the application, you may want to have, this community engaging, right? For example, if you are a machine builder in industry or a machinery vendor, right? And you want to have an active community, deploying applications. Well, in industry, people are more conservative, but this may have in the future. You might want to go, with a board that has a community around it. And then I would benchmark, power efficiency if this is a concern, because if it adds up, it makes a difference, right? Then, I/O connectivity requirements. So I wouldn't say that there is a single answer to the question, right? It's actually a matter of taking your business requirements, seeing the trade-offs you have to encounter, because sometimes, as I said, you have conflicting requirements like availability of data points versus real-time requirements or bandwidth and storage efficiency. So I think it's a matter of benchmarking and then making the right design that you solve the trade-offs. Also, TinyML and embedded machine learning, because they are quite new terms, they are having different scopes by different people, right? In my presentation, you perceived right that TinyML deploying something on a microcontroller, but I would, if somebody calls TinyML a machine learning running on an embedded device like a data collection, or a smart meter or a data collection device in a factory, I would still accept this definition. I don't know if there are any other questions for the speakers. I think we are just 2 minutes before concluding. I would like to thank everybody for staying, your 56 guys that you stayed along for the whole duration of the seminar. I would like to thank the speakers. I would like to say that the slides and the recording will be made available in the project websites, but also in NG-IoT and the EU-IoT website. We will take the freedom to notify you, to all registered participants when these are available. We will take the freedom to invite you in upcoming seminars that we are organizing again on niche topics. So just to whet your appetite, I think we've got the next seminar in 1 month or so, will be on tactile aspects and also tactile internet aspects, also augmented reality, virtual reality, and how these are changing the landscape of IoT and industrial applications. And then we're going to have also other topics like blockchain and decentralized intelligence in the IoT context, 5G architectures and 5G technologies and their impact on future Internet of Things applications, a workshop on Internet of Things architectures, from reference architectures to customized architectures to address all these topics. So we've got rich content coming, and we will take the freedom, contacting you, for future seminars and for the availability. So yes, that's all from my side. I don't know if any one of the speakers wants to say something. Otherwise, I would suggest that we conclude this seminar. And again, I would like to thank very much all contributors, because I'm in this community many years, and I have to confess that the content shared was really excellent and was really very high quality, and the seminar was really very interesting, in my opinion. Are there any comments from other colleagues? If not, I'd like to thank everyone, and we can stop the recording, and looking forward to seeing you all soon online, but also in the first occasion in a face-to-face workshop.
Thank you very much for the organization.